Okay, I think let's get started. Welcome everybody, my name is George Dunlap, and today we're going to be talking about nested virtualization. Hopefully you want nested virtualization, not Zenalize. Anyway, so just a bit of background. Nested Virt, Nested HVM was implemented both for AMD and for Intel back in the kind of 2010, 2011 timeframe. But, I wouldn't mind one. But it has always been considered kind of tech preview. It's never been considered something that you would want to sell to customers. Definitely never considered something you would want to allow, you would rely on for security. Not yet? So I'll just hold this here and eventually it'll...
There we go. Okay, there we are. That said, it was often quite usable, at least through kind of 2018 when I was using it to test the Zen CentOS packages. But it broke sometime around 2020, and in November of last year, I started to look at it to try to figure out what state it was in, and if we could get it to the point where we could actually security support it and let other people actually make it the kind of thing that we could sell to customers. But, as you may have heard, I'm kind of moving on, doing some my own thing. So this talk is an attempt to kind of do a brain transfer of what I've learned in the last couple of months. So my goal is to help you guys to be able to deal with nested HVM. Hopefully someone in this room, someone in the community, will pick it up and start actually writing it. Some of you will no doubt be reviewing it. Some of you will be finding bugs in it and trying to fix them. So obviously to do that you'll need a very detailed understanding of the manual, which is very large and detailed, and of the code itself. So I'm not going to dig into that, but what I want to do is to give you kind of a map of the territory, as it were. A high-level overview, somewhat simplified, so that when you find yourself in the manual or in the code, you have an idea kind of, you can orient yourself as to what actually should be going on. I've also, in the short time that I've been here, discovered some kind of, some weaknesses, some kind of areas to be, here be dragons kind of things. So I'm going to be, hello? Oh, sorry. Yeah, so what's going on here? Right, so to do that, we're going to first, and this talk is going to be actually in two parts. I really couldn't fit more than the first kind of half of this into half an hour. So we're just first going to talk about why use nested virtualization, what do we want it for in the first place. We're going to do a brief overview, slightly more detailed than normal, much less detailed than you would than you need to, from the manual to implement it, of what the hardware actually is, okay, how you can use how you virtualize the CPU, and how you virtualize memory. So for the CPU stuff, we're going to start by focusing on AMD. Between AMD and Intel, the implementation is quite similar. There are some key differences that Intel has. The AMD is a bit easier to understand, so we're going to start with that, and then we're going to expand into what Intel does later. After we've covered the basics of what it is that we're going to try to virtualize, we're going to go into what it means to virtualize that, and a sketch of how that happens inside Zen. Then we're going to take a brief detour to talk about the differences that Intel has. And then probably in part two, definitely, we're going to go over some of the pitfalls and the future work. So, why use nested HVM? So the first obviously thing that we could use, we think of as developers, is for testing. I believe that Mark has actually had some success in testing Zen inside of KVM, nested. And I certainly use that for the test of CentOS Zen packages. And there's just a lot of situations where, so obviously in most of the situations, we definitely need to test Zen on real hardware because the real hardware has concrete effects. That said, there's a lot of situations. So for instance, if you were trying to test your high availability features, if you have say a pool of resources, pool of different servers, a lot of that stuff happens in ring 0 and doesn't actually depend on the particulars of the particular hardware that you're running on. So it can be actually useful to be able to, on a single physical machine, boot up 20 or 30 Zen server hosts, put them together in a pool, and do different things with them. Okay, it gives you more control over the situation. Booting times for VMs are a lot faster than booting times for enterprise test hardware, and so on. But the bigger thing from Zen server's perspective is Windows virtualization-based security. So Windows has started using the HCM features for itself to give itself advanced protection things. Okay, so there's things you may have heard of like credential guard, application guard, memory integrity, and so on. All of these things use the hardware virtualization features for Intel and AMD, which means if you're running Windows virtualized, you have to have nested virtualizations to enable these. And just like a few years ago, Microsoft at some point said, look, to run Windows 11, you need to have a TPM. And at that point, basically, Zen server had to scramble around and make sure that we had a TPM in time for that, so that we could run Windows guests. Similarly, there's a fear that at some point in the future, Windows will say, right, Microsoft will say, to run Windows 12, you'll need to have hardware, you need to have hardware-based security. And so then we want to be able to make sure that we have that stuff in a good place to start from before that announcement is made. Okay, so now we're going to, sorry. The clicker's not working very well. Do a brief overview of what the hardware actually gives you. Okay, so here's generalized system. We have, a physical machine with CPU and memory. We have a host. This is Zen. It wants to present the illusion to a guest that the guest has CPU, memory, devices all to itself. Now, devices, I think, is a pretty solved problem. That's kind of out of scope for this talk. But what we're going to talk about in this talk is how to virtualize the CPU and the memory. So what Intel and AMD introduced back in the early 2000s, they retroactively renamed the normal operating mode of the processor to call root mode, and they introduced a new mode called non-root mode. Okay, in non-root mode, the CPU executes just as normal, bug-for-bug compatibility, but events of interest to a hypervisor can be intercepted. So how this is done is, so again, we're talking about the SVM here. So you have a VM control block. This is a 4K page where on the AMD side, the contents of it are defined for you. So there's a guest state area, there's a host state area, and there's a control area that has intercepts where you define what events you want to be informed about as a hypervisor, and ways that you can change the behavior of how the kind of virtual processor executes as it's executing. So what you do when you want to run an L1 is you write into the VM control block the guest state that you wanted to start running in. You set the intercepts that you want to be told about, and then you execute what's called a VM run. The hypervisor, so the hardware will then copy the host CPU state somewhere, probably into the VM control block, but as explicitly said, it might be anywhere. And it copies the guest state out of the VMCB into the CPU state, and it begins to run. And then it runs just as normal until one of the events happens that you've asked to intercept, at which point a VM exit happens. So the guest registers are stored back into the VM control block for the hypervisor to use. The host state is loaded back in, and there's information about the event that caused the VM exit is stored into the VM control block so that the hypervisor can then take the appropriate action in response to that, and probably do a VM run again, and so on. So the next thing to cover here is how do we, so that's how the hardware allows you to virtualize CPUs. How do you virtualize memory? So if you call the host has its own memory, the guest is beginning the illusion of having its own physical memory as well. So in virtualization, we call the memory that the guest thinks of as a physical memory as physical memory, or guest physical memory, and we call what the host thinks of as a physical memory as machine memory. Okay, that's terminology we've inherited. That's what we're going to use. So obviously, the actual processor, in order to do any operations, needs to use the machine physical addresses. So you have to convert the guest physical addresses into machine physical addresses somehow. And this is done with a P to M. Now, the hypervisor will have a mapping, its idea of the mapping of the guest physical addresses to the host physical addresses. And there's many different ways to do this mapping for the hardware. But the one we're going to cover today is called hardware-assisted paging. Okay, so this is HAP. On AMD, it's called NPT or RVI. On Intel, it's called EPT. On some places, it's called second stage translation. But basically, you may be aware of that. For normal operating systems, we have the ability to translate virtual addresses into physical addresses using page tables. Okay, so the guest operating system will set up page tables that map the virtual addresses to the physical addresses, and the hardware itself will walk the page tables and convert and do that conversion. Okay. In a similar way, basically using the hardware-assisted paging, the hardware itself will convert the guest physical addresses into machine physical addresses so that it can then be used. So what the host does is you store the P to M in the format which is appropriate to be used for your hardware. So basically, if you're running on Intel, you store your P to M in EPT format. If you're running on AMD, you store your P to M in NPT format. And then when you go to set up your VMCB, you simply point the root page table to the P to M that you already have and let it run. And the hardware will do all the translation all the way from the virtual addresses through the guest page tables, through the P to M, down to the physical addresses so that it actually can access the page that you want to access. Okay, so that's what we're trying to virtualize. Are there any questions about that so far? Okay. So now how to virtualize this. So to begin with, things are going to get confusing. Okay, so in this picture, we have two guests and two hosts. Okay, so we have to introduce a consistent terminology so we know what we're talking about. So the thing which is running on the bare hardware is always going to be an L0. It could be an L0 operating system or an L0 hypervisor. Anything that is running on an L0 hypervisor is called an L1. It could be an L1 operating system, an L1 hypervisor. Anything that is running on an L2 hypervisor, on an L1 hypervisor is called an L2. Okay. In our case, we're going to be primarily talking about an L2 operating system, but in theory, there's no reason if the nested virtualization is implemented properly, there's no reason we couldn't stack them arbitrarily deep as you have the tolerance for the performance overhead. So obviously the L0 has its own VM control block, and because we're actually going to have a lot of VM control blocks, we're going to call this VMCB01. So this is the VM control block for the L0 to use for the L1. And the L0 obviously has its P to M. It's translating the L1 physical addresses to L0 addresses, so we're going to call that the P to M 10. Okay. Now, the L1 wants to be able to provide virtualized CPU and virtualized memory to the L2. So it's going to want to have its own VMCB. We're going to call this, from the L0 perspective, we're going to call this the VMCB 1.2, the VMCB in the L1 for the L2 guest. Okay, and it's obviously going to need to provide a P2 level 2 physical addresses. And so it needs, it's going to want a P to M that maps the L2 addresses, L2 guest physical addresses to the L1 physical addresses. And what the L1 wants to happen, of course, is it wants to be able to execute a VM run, set up this stuff, execute a VM run, have the L2 run, and then get a VM exit. Okay, so that's what the L1 wants. So how are we going to virtualize this? So what the L2 does, what the L0 does, is it will set up its own separate VMCB and P to M. Okay, so there's essentially a virtualized root mode, virtualized non-root mode. Okay, so when the L1 executes a VM run, it actually exits down to the L0. The L0 will either create or update VMCB 02. So this is the VMCB from the L0 to the L2, okay? It will copy the guest state from the VMCB 12 into the VMCB 02. It will kind of set up the intercepts, and the intercepts will be essentially a merging of what the L0 wants and the L1 want, okay? So if either the L1 or the L0 wants to be told about an event, then that has to be intercepted in the VMCB 02, okay? And then similarly, the hardware needs to have, it can only do one level of mapping. So all the addresses all the linear addresses that are going to happen in the L2 are going to happen in L2 physical address space. So the hardware needs to have a mapping of the L2 physical address space all the way down to the L0 machine address space, okay? So we have to have a separate P2M, a P2M 20, which maps the L2 physical addresses all the way down to the L0 physical addresses, okay? So the L0 will sets this all up, and then do a VM run. And the L2 will run for a little while, and when it does a VM exit, then so when the L2 exits to L0, at that point the L0 needs to figure out, this VM exit, is this something that I need to pass straight back on to the L1? Is this something that I can handle myself and just return back to the L0, return back to the L2? Or is it something where I need to do something a little bit and then I need to pass it on to the L1 to do the rest of it? If we need to pass stuff back to the L1, then we need to copy the guest state, the L2 guest state from the VMCB 02 into the VMCB 12. We need to write into the VMCB 12 what caused the VM exit from the L1's perspective, right? And in some cases, we'll just be copying stuff straight out of the VMCB 02 into the VMCB 12, but sometimes from the L1's perspective, what caused the exit will be different than from the L0's perspective, what caused the VM exit, okay? And then we're going to do a VM run and resume the VMCB resume the L1, and it can continue doing whatever it's going to do. Okay, so that's our picture, the high-level overview of what we're trying to accomplish with Nested Virt. Are there any questions about this? Yes, Mark.
I'm sure you will cover it later, but how you keep VM?
Yeah, so I think at the moment, at the moment, basically, I think that essentially every time we do a flush, we throw away this P2M. So both of these are what's called derived, right? So the L1 stuff, that's constant, the L0 stuff is constant, and at any point you can derive these things here from those things. So at the moment what happens is basically you start the P2M 20, it's just empty. And then it'll access a bit of the L2 physical address space that will cause a nested page fault back out to the hypervisor at the L0. The L0 will look at the P2M 21 and say, oh, this entry is actually valid, and it will translate the P2M 21 into the P2M 20 and then resume the guest. So that's an example of a situation where basically you're ping-ponging between L2 and L0 as it slowly fills in the P2M. And then basically, like I haven't looked in too much detail, but I think for the most part, right now, the implementation of you call it shadow P2M 20, I think it's fairly done. And I'm going to talk about that a little bit in the second half. But yeah, basically, I believe at the moment, and then whenever you do what's called an EPT flush, I think you just throw away the whole page table and start over again, which is obviously quite slow and kind of wasteful. The P2M table doesn't change that much, so it's probably not nearly as bad as the shadow paging, but I'm sure that it could probably be improved. Yes?
Yeah, I have a question too. Does the hardware have some support for this nested virtualization? Because as far as I understand, this all is done by the software in L0 hypervisor. Does the hardware help somehow to accelerate the path?
I don't think that I think that the only, there's some particular things about Intel which make it more difficult to virtualize. And so there's support for those specific things, okay, which I'm going to get to in the kind of next section. But I don't think there's any specific hardware that helps this kind of translation. Does someone want to contradict me?
There's
Yeah, that's for Intel.
virtualizing.
Yeah, that's for Intel. So we'll get into that in a bit. Yeah.
Are you sure that this is for Intel? Because I recently backported a patch to a kernel for SVM.
Right. Okay.
So SVM is AMD, of course.
Yeah. So there's a bunch of these kinds of things. There's also support for nested, virtual interrupts and different things like this as well. So there are some support for these sorts of things. But I think there's not support for the kind of, as far as I'm aware, of like doing like 2 levels of the nested paging. Yeah. So, okay. Yes, Debbie?
What kind of overheads can we expect from nested virtualization?
I haven't done any tests. And I think, as far as I can tell, like I don't think it's been basically optimized at all. So I'm sure there's a lot of low-hanging fruit
What
there.
about, I see, does this basically work because the L1 has to flush the second, also, is there some at least hardware support for at least caching P to M translations separately from stage 1 translations so that you don't take, so that when you take a P to M, so that when there's a TLB, basically so that TLB misses don't take like 24 loads?
I believe that there is some caching, but you'd have to ask some. I mean, that's all under the hood. So you'd have to ask someone, a hardware engineer, to more about that.
There is caching. It's exactly like for the virtual to physical translation. There's caching also for the physical for what goes through the
Yeah.
VPN. And there is, in fact, merged translation caching as well.
Yes.
On Intel, I think also on AMD.
Okay.
Okay, so that makes it much faster than you'd likely expect.
I mean, yeah. So basically, it could be worse, but in the worst case, if you have a pathological workload where you have a lot of TLB misses, a lot of second stage misses, then yeah, it's gonna be pretty bad. Okay, so let's get to the Intel stuff, and then we can do some more questions, basically. So last thing before we kind of finish this part of the talk. On AMD, you're just given a block of memory, and you're told the layout of the memory. You just write to the memory, and then you do a VM run pointed at that memory, and the CPU kind of figures out everything. Now, as you can imagine, there's actually a lot of stuff in here, right? So you not only have all of the potential guest state that you may have to load, there's also a load of different things you may have to look at as far as like what intercepts to do, what kinds of I/O ports to intercept, what kinds of MSRs to intercept, or CPU IDs, and so on, right? Actually, a lot of information, and from the hardware's perspective, any of those things may have changed between the time you did a VM exit and a VM enter, right? But, of course, in the vast majority of cases, you're going to do a VM exit, you're going to twiddle a few minor things, and do a VM enter right away, changing almost nothing, right? You're going to change very little between the time you did the VM exit and the VM enter. But how does the hardware know what you changed? It still has to, at some level. I mean, AMD has some ways that the hypervisor can hint to the hardware that it can skip certain bits of it. But still, it has to do a lot of sort of going through this large amount of memory to figure out what may have been changed since the last time you entered, right? So Intel decided that they were going to try to make the interface, so AMD made it kind of the interface easy for the operating system, but a little bit harder for themselves to be efficient. Intel decided to make it a little bit easier for the hardware and a little bit more difficult for the operating system. So Intel have a thing called the Virtual Machine Control Structure, and so the VMCS rather than VMCB, and you're not allowed to write to it directly. So once you tell the processor this is a VMCS, from that point on you're not allowed to touch it, read or write to it. Instead, directly, you have to use these special VM read and VM write instructions, and you VM write, giving it basically a kind of a more abstracted number. So like this represents ECX, and then the VM write instruction will find the right place in the VMCB to actually write that. But that does mean that the hardware can intercept. It knows what part of the VMCB has changed, and in theory, if you do a VM exit, change only 2 or 3 things, then do VM enter, then it can know I know that the hypervisor only changed these three things. I don't need to go through the whole VMCS to load it up, and it could, in theory, be more efficient. Now, I'm not sure how much efficiency that actually gained, Intel over AMD, but I do know that from a naive perspective of the virtualizing that, it makes it a lot more difficult. So version 1 of Nested VMX, you had to take a VMX, every time you did a VM read or VM write in the L1, you had to take a VM exit all the way out to the L0, do something or other, and then go back, right? So you can imagine this is way, way more expensive in the L1 than simply doing a bunch of writes and then copying stuff over, right? So they introduced a piece of hardware, feature fairly early on called Shadow VMCS, okay? And this is one of the reasons why we have to say VMCS 202 instead of Shadow VMCS, because this was kind of stolen by Intel first. Basically, this is a way that you can mark a VMCS as this is being used by an L1. So the hardware, if a VMCS is marked as Shadow, the hardware is not allowed to use it as an actual VMCS, okay? But the L1 can execute VM write instructions into the VMCS, and it will just happen natively. And then once you exit to the L0, you can also use the VM read and write instructions to see what the guest has written and so on. Yeah, so the other thing about Intel is that in AMD, the vast majority of the features are exposed to the guest via CPU ID. So on Intel, a large number of them are exposed via MSRs. And this actually will cause problems that we'll discuss in the next talk. So with that, are there any questions? Yes, Edwin.
I have a question about VM exits. You said you have to handle it in L0. Are there any cases where you can let the L1 handle the VM exit directly, or do you always need to intercept all of the L1, L2 to L1 VM exits in order to change the VMCS?
I don't think there's a way. I don't think there's a way to get to exit directly from. So what you would have to do. Sorry, actually. Right. So this is our kind of summary. What you would have to do then is you'd have to somehow exit. You'd have to have the hardware exit directly from the L2 into the L1. You'd have to have the hardware write the appropriate things into the VMCB, 1, 2, and so on. And the other thing is that, and you would also have to distinguish between, the L0 would have to somehow say, these things you can let these things I need to know about, these things you can deliver directly to the L1. So I'm not really aware of that kind of hardware being available. Yeah.
So then you need to take everyone and then you VM write to update it to L0. So you need to observe all the VM exits.
Yeah, because each VM exit, you have to, the L0 has to decide what to do with it. So, Marek?
When you use VM read to VM write, hardware gets information access. If you use this shadow VMCS, do you get the information what L1 had written into VMCS? Like what is changed?
I don't think the L0 does. No. So basically, I think your choices are you can take the hit of all the VM exits, or you can take the hit of like having to manually compare which was what changed or not.
SSVM has the clean list feature for some parts of the VMCB.
Yeah.
But VTX has nothing equivalent.
Okay.
Wait, can you use the access dirty bits in the P2M01 for that?
Well, it's just one page. So basically, it would tell you. Yeah. I mean, I guess in theory, if you wanted to, you could try to use debug registers to do sub page ranges or something like that. But that doesn't sound like fun.
You can tell if nothing's changed.
Yeah, I guess you could tell if nothing's changed. But the other thing you could do is you could trap on the first VM. You could basically not have the VMCB set, and the first time the L1 does a VM write, then you trap to the L0, give it permission, and then go back. So then you know that something has changed. you know the first thing that was changed, but you don't know what else was changed. Yeah. Any other questions? Okay, well, meet me back here in an hour or two to hear what the rest of the talk. Thank you.